Hello, everyone. Welcome to the first binary episode of the podcast back from our summer break. I'm Spectre, with me is Z. For those who missed yesterday's episode, welcome back, everybody. If you want to hear what happened over the summer and some casual discussion, we did about 40 minutes of it or something on the last bounty episode.
Yeah, it
So
went
if
a
you're
little
interested,
bit
check that
long.
out. It
That was
did.
a bit longer of a discussion than I expected. Yeah, I talked a bit about DEF CON itself, and you talked about your hardware I/O experience. Your talk there, so we won't rehash that discussion here.
Yeah. But it was a fun discussion, and yeah, there was a fair amount to talk about, even though we went 40 minutes, but we did talk about a fair amount of different stuff. Hardware IO was a pretty positive experience, and I will shout out that we're planning to do some coverage streams for the Hardware IO talks, and the reason I mentioned that on the binary episode again is because a lot of the talks that were done at Hardware IO were more low level, so it's more akin to what we'd be covering on these types of episodes. But yeah, aside from that, there was quite a bit of interesting low-level posts that were released during the summer. Some of which we'll cover today. I think some of them will push to next week, and it's a mixed bag of things, including a fun TPM take, AI-powered fuzzing, some in the wild stuff, and more. TPM stuff will be interesting to talk about since that's somewhat close to what I've been putting a lot of work into on the side, which is the PSP reversing. Some of you might have been with us for the stream I did on Sunday, where I was reversing the PSP firmware, including loading of the Secure OS, which is used to facilitate TPM on AMD devices, along with other things. Before we get into topics, though, as always, I'll let Z get into the spot the bone solution.
Yeah, so this week's Spot the Vuln is actually one of the vulnerabilities that I put together quickly for the Spot the Vulnerability t-shirt. So if you want to check that out, that is over on our blog on how to make one of those because I couldn't actually sell them. Just all the assets are there. It takes a couple minutes, enter the values, and get it shipped out. This is one of those vulnerabilities. So core idea with it is you have this get function that takes in a URL, and it just checks that the URL has a regex match to this regex or allow regex, which is a caret at the start indicating, has to start with what follows or matches the start of your token, HTTPS, safe domain. So basically just checking, yeah, that whatever URL you provide is trying to access their whitelisted API domain. So more or less makes sense. Problem is, and this is a common problem in regex, common problem in validation, are these dot characters. Period character in regex is a wildcard character. I have used this in a spot the vuln before. Unfortunately, I was a little bit lazy on getting it up this week. But because that is a wild card, basically any character can be there. It doesn't have to be a period, so you can register like API to safe domain without a dot in there. And that too will match where the period is, allowing the whole regex to pass, and you'll be able to make a request to an attacker controlled location. You can set that to whatever like IP you want. It will have that domain, so how you use it will vary, but you can get the request going somewhere outside that, like metadata. Service would be a common target because you controlling the domain, you do control the IP. But that is a restriction where you're not controlling, or you don't have proper control over the host. I guess I'd say you do technically control it, but you can't just send it off to an arbitrary one. Actually, I'm not sure offhand if request is going to follow redirects. It might, in which case you can, redirect off where you want. Um, yeah, I'd have to look into that one. That just came to me, but regardless, the main bypass here is just the wildcard in the regex. It looks like a URL, so oftentimes it doesn't click that there's a problem here because the periods are correct for a URL. They just need to be escaped so that they're actually treated as literal period characters rather than the wildcard character.
All right, so we'll jump into our topics. Up first, we have a post by Google on AI-powered fuzzing, and this is something we talked about a little bit before the break. This idea of merging machine learning with fuzzing, as it does sort of make sense as an application for it, compared to some of the other ones that have been tossed around. But yeah, Z, I'll let you jump into this one.
Yeah, and I added this post actually before I ended up watching the DEF CON talk that I spoke about. or added this to like our scheduler that we used to plan the episodes before I had seen that or watched that DEF CON talk. Because I talked about a DEF CON talk that was basically about or using LLMs and fuzzing. And this is just Google basically applying that same concept where they're taking the LLMs, and my thought with a lot of AI and fuzzing has been that it doesn't really generate much that you can't do deterministically. It just introduces a bunch of non-determinism to what we already know, like with a lot of generating specific test strings. It's going to be non-deterministic in what's generating, and we already kind of know the test cases to be testing for. Like, um, yeah, it felt a little bit like it was the wrong application. That said, one of the places where even I've been using AI has been to generate code, using it just using Copilot for myself. Have that in the IDE. It'll generate just some code for me as I'm writing it, saving me a few seconds here, a few seconds there, which adds up. So what they've looked at doing here with the LM aided fuzzing is they're using the fuzzing to generate the code as part of like the test harness. They're actually generating some of like the test cases and all of that, which is, I think, a good use for this. It is something that LMs have shown themselves to be able to do fairly well. And I actually remember a research paper we talked about quite a while back where its focus was basically on training on I think it was the regression tests for Chrome. Might have been all the tests in general, but I remember the regression tests at least getting called out, which I thought was a really kind of fascinating area to train on, having it test based on previous errors effectively and using that to try and generate code that looks similar, being an LM, generating that type of code and generating test cases that may not necessarily lead to that regression or showcase that regression, but finding more bugs that way. And they actually had some success there. So I thought it was interesting to see Google taking the approach of actually trying to automate fuzzing and using LMs to generate these cases and like integrated at that level. Because I do think it is a good use for fuzzing here compared to some of the other, or a good use for AI, sorry, compared to some of the other applications of AI that that I've seen. Question in chat from I'm Web3. Is there any AI that can turn binary into source code? I, that tends to be, that's one of those things that feels like it can be done deterministically, where you have the code patterns and turns it back into source code. We've got decompilers that approach doing that, and I'm not sure if like the non-deterministic nature of AIs, at least as I've seen them, I'm not like an AI expert, so maybe you do have like really deterministic AIs. I know you can like tune the LLMs to, set their temperature to 0 or something, making them more deterministic. But regardless, it kind of feels to me like that just isn't the place to apply AI. That said, what there is it Ghidra GPT or something? No, I forget what the name of that project was. There was one that integrated into Ghidra to try and like add comments, I think, onto the functions it detected. So it wasn't going binary to source code. I know with the LLMs testing binary to source hasn't been good, but doing some work at either smaller assemblies, explaining this assembly sort of questions, or taking the function and having it kind of do things there has been somewhat effective. On the Spectre, do you recall the Ghidra project I'm thinking of?
Yeah, I was just looking into it. It might have been G3PO, if not.
That does sound right.
Yeah, I think it was that. Yeah, I mean, AI in the context of reverse engineering, some people have played with it. It can work for trying to recognize patterns and whatnot in some areas, but I don't think it works super well. Generally, with AI, like a lot of the training has been going the other direction, right? Like writing code, not trying to reverse uh, binary back into source code. So maybe it could be done with enough trainer or something, but I don't think that's really been where a lot of the research has been focused on. But
Yeah, to me, like it doesn't feel like the right application of it. Although I could see a reason why you'd say, like, no, okay, you've got like a very consistent, like statistical representation where statistically, like this set of instructions should lead to this source code. So I could see a reason why you might think like you'd have that statistical connection. Therefore, you could probably have this machine learning done in there. So I don't know. It feels like something that could be done. It hasn't been done terribly successful right now, though. But on a whole, like outside of being a lot more scalable, which jumping back on the Google thing here, that is kind of a big thing. Their goal is this fully automate fuzzing. So being able to generate like your fuzz targets using LM does make sense as like a use case. A lot of other things that we've seen applying AI, and there has been as part of been more just a cog in the machine. Maybe as part of the mutation aspect where it would mutate test cases or something like that. And back on the question about reverse engineering, yeah, the I think I just pulled it up. Actually, there now it's gonna now the link should show up in our show notes. But this G3PO thing, protocol droid for Ghidra that use looks like they're using the GPT 3.5 turbo to try and do some of that generation automatically. It's not quite what you're asking for on Web3, but it's about as close as I can think of.
But yeah, on the topic of fuzzing, I agree that not only is it an applicable case of doing the test case generation, but it also feels like a good place to put AI just because it's something that's going to have a fairly high impact, I think. And for the most part, the human involvement on writing harnesses and stuff is just very tedious. Like I don't know if there's many people out there that really enjoy writing fuzzing harnesses, um, or like writing initial test cases for to get mutated. And coverage is like a pretty big metric for like a lot of the times when you have bugs that aren't found by fuzzing, it's because the fuzzer wasn't targeting that code. It just didn't have an input that was modeled for that area. So I think putting AI here can be a pretty effective use case of it, and it's not over the top ridiculous of what you're expecting it to do. It's just like, hey, can you write some test cases to hit this area of code? Um, and then let the fuzzing process take it from there of mutating and all that. So yeah, I think it's a pretty cool idea. It sounds like it's been fairly useful. So in their blog post, they mentioned that they've been testing it on the TinyXML2 library. Um, they did have some trouble where initially the harnesses that they generated with like the prompts would fail to build, but after enough iterating on the prompt engineering and whatnot, they were able to get it working. And they stated that replicating creating those harnesses manually would have taken like about a day's worth of work at least, which doesn't sound like a lot on its own, but it does add up, especially when you're talking about multiple subsystems, multiple projects. um, that time could really add up. Toward
Yeah,
the end of the post, they state they would like to try to get more fully automated fuzzing eventually, like being able to set up initial fuzzing on targets without any manual work, and getting it working on like non-C based projects. But yeah, it seems for now they're keeping their goals modest, and it seems like it's pretty promising.
yeah, I can definitely see this also being used. I like they mentioned getting towards it, but the use case just with other languages, running test case, especially on something like Python, which is a little bit more flexible in terms of what it accepts. But yeah, it does feel like uh, one of the aspects of AI that I more or less just overlooked or would just dismiss was the scalability aspect. Yeah, this only maybe saved a day at a time writing those harnesses or whatever. Like it's nothing crazy, but if you are trying to apply this over, hundreds, thousands of projects, that's going to add up to quite a few man hours. Just, I mean, part of that is just reading the code to understand how to call things. So when you have the LM kind of able to digest the code base and then generate something, um, that's saving quite a bit of engineering time to just generate that. And that scalability aspect of AI, I think, is one aspect that I often just dismiss as like, whatever, we could do this more, more deterministically, more like intentional focus. But no, the scalability, I think, is the big thing that's coming from this.
Yeah, agreed. And continuing on the Train at Project Zero posts, Project Zero also made another post in August on MTE. So MTE is another favorite of ours. We like to talk about it a fair bit because, as far as memory corruption goes, it is a fairly significant mitigation, or at least that is the idea. And Project Zero put out a post basically summarizing their conclusions after looking at MTE and looking at different issues that it might have and theorizing on some bypasses. So yeah, this is from Mark Brand at Project Zero. The initial post here is really short, like probably the shortest Project Zero blog post, but they do link off to more detailed analysis, which are like quite a bit longer and have a lot more meat into them. So, Z, I'll let you get into it.
Yeah, I mean, this initial post is short because it doesn't really say much. It does make two important comments though. MT, or this is quoting it, MT is still by far the most promising path forward for improving C/C++ software security. And the other thing being no MTE based mitigation is going to completely solve the problem of exploitable C and C++ memory safety issues. Two statements, I think we generally would. Like, I can't imagine anybody here is really going to disagree with those. Maybe disagree on it being the most promising path forward if you want to push Rust or something there, but sticking with C++. It has been one of those things that's been looming kind of on the horizon. When we talked about when we did our video about kind of like the future of exploit development, I know that was something that was kind of looming there along with CET from Intel as, being a bit of a gray cloud off in the distance. Kind of looking at, what is this going to look like when it lands? Because there's a lot of potential for it to be rather impactful. And I do think it will be impactful, but the more we've actually been seeing it land, seeing these things, seeing these mitigations land, the more it's become clear that yes, they're going to have an impact, but no, it's not really killing much off. But they will have an impact. So we do have Spectre mentioned kind of the three posts. I think the first post, like if you just want to jump in this and kind of get a look at, here are some of the big picture issues that they kind of see with MT, and kind of get an understanding of what they're thinking about. It's just the first post, which is their implementation testing. The second post, the mitigation case studies, really just takes the issues that they introduced in that first post and then apply to an actual case study, looking at I think it was Chrome, some aspects of Chrome, and just looking at like what impact would MT have given the fact that we know about these issues. And then the third one was like, how can they specifically implement this into the kernel, and what issues are there. So I'll jump in here with the first post on implementation testing. So one thing that isn't, it's actually covered, I think, in the second post where they explain what sync and async means. I thought was a little bit weird. Yeah. So they talk about in the second post, though, it does matter for this first post, which is synchronous MT versus async. That is on ARM with this implementation. There's kind of two ways that MTE can run, either being synchronous, where when like an instruction has this invalid access, and I guess I should also mention like memory tagging, adding like a little 4-bit tag onto pointers. So when you try and access a pointer, it knows that tag. So if you try and access a memory that should be tagged as like something else, um, it'll basically just know like, hey, this pointer shouldn't actually be going to this address or whatever, and it'll block your access. So it can block that in one of two ways, either being synchronous mode where the instruction itself having that bad access will just fault, and the asynchronous mode, which is less secure, will basically just set a per core flag saying, hey, an invalid access happened, and then the kernel will be responsible for actually checking that flag and doing something with it. Um, and so they actually do talk about how that could be taken advantage of, but that is also just going to be generally recognized as a weaker option. So jumping back on the first post, where they talk about some issues here, they also present kind of the concept of soft versus hard mitigations. Soft just being a mitigation that um, you can develop a bypass for and then reuse it either in a new exploit or with a new vulnerability or something like that, versus hard, you need to reinvest it every time. Um, giving the example of like building a ROP chain. You can, in theory, do that once. I mean, you might have to make a few adjustments on the early stage of it, but you can kind of write your ROP chain. It does whatever, and away you go. On every vulnerability, you can just reuse more or less the same thing. Versus like ASLR, you always need to recreate like a new information leak every time. You don't just get to reuse it. Although they even mentioned that like with some primitives in some areas, like you definitely can just have a generic technique that given this primitive, you turn it into an info leak this way, in a sense, making it soft. So they present that, which I think is at least an interesting approach. I'm not sure if I'm really going to adopt that soft versus hard, but it is terminology that I haven't seen anywhere. And they
Yeah, I
also
mean, the
call
way
it,
I look at it is like hard mitigation is something that would typically require an additional bug to chain with. Um, so yeah, like you said, I haven't really seen anything try to coin those scenarios. Um, but I mean, it's a fair way of looking at it. The soft and hard mitigation idea. It's difficult to like exploit scenarios are difficult to pin into buckets like that, but it's a fair attempt at it, I think.
yeah, I think we've often ended up talking about it more in the sense of early versus late stage mitigations. I think when we've split up mitigations as being like one or the other. And it doesn't quite map onto this. Uh, but it also kind of does, where an early stage mitigation would also kind of be that type that's going to require another bug to get through, whereas late stage you're just kind of like late stage feels like it would match more the soft. So I don't know. That's the terminology we've definitely used on the podcast before. I wanted to spend a little bit of time though talking it out, like what they've kind of coined here, because Project Zero does kind of set the standard a lot of the time. So I wouldn't be surprised to start seeing it used more often. And they also call out a solution being something that eliminates exploitability. And as already mentioned there, MTE isn't a solution. So with all like that nice background terminology out of the way, actually getting into some of the issues that they've come through or noticed here, they do start off just talking about the hardware aspect of MT with questions like, does MT block Spectre? Which no, it's still going to speculatively execute over checking the pointer's tag. Um, and so because of that, like it's not going to block Spectre, and they even call out if you wanted it to actually stop speculation on a tag check, that actually just creates a side channel for attackers to use speculative execution to determine if a tag check was successful or not. So kind of backfiring if you try to add that in. They also look at if it has an impact on the window length, which would be another side channel you could use depending on how far speculation went. You could use that to determine if the take check passed or failed. Game they figure that they probably can't. But they do kind of talk a little bit about this hardware stuff, which you can dive into if that's of interest to you. And then they get into what I thought was the more interesting area, which is the software aspect of this. Um, Mostly dealing with like specific implementations of like the userland MT. So there could be variations there. This isn't going to be everything that uses MT does it exactly the same way. I believe what they basically said that issues 1 and 2 here are just going to be kind of quirks of how things are implemented in the kernel right now. Um, and the fourth one is just like a more fundamental weakness. And then the third one is, well, I guess let's just get into them. One being handling of syscall arguments. It's actually 1 and 2 are both the handling of syscall arguments. Um, Problem being when you're running in async mode, and a syscall argument comes in, effectively the kernel is not going to catch any of those invalid accesses from or with the user space pointer that was provided. Basically, kernel's allowed to access whatever. So when reading that data, it's just basically going to let it through on a async call. Um, on the sorry, lost my place in my notes. On the second one, in synchronous mode, while the syscalls won't work, they will when you're running in synchronous mode. That instruction will fault, and you will get an error. The kernel isn't going to crash on you because the kernel, of course, doesn't want to just crash all the time. So what the kernel is going to do is it's going to return an e-fault, which unfortunately then means that can potentially be a way an attacker could leverage, make a syscall using a pointer that they're unsure about and find out, does it pass or does it fail? If it fails, then then you can know that the tag check failed, giving you a bit of an oracle to know about your pointers without actually needing to crash the process itself.
Yeah, you can basically brute force the tag.
Yeah,
Because your space
your
is pretty small at only 4 bits.
4 bits, which gives you or only 16 values.
Yeah.
Or 16 max values, which is another thing I should mention with MT. A lot of its protection, like I mentioned, when you have a pointer, you're trying to access data that should be tagged to something else. Um, it's probabilistic. It's like a 1 in 16 chance that you're going to get it right. Um, it's not like every time you access it's just going to detect it. You do have that slight chance of getting it right. So depending on the scenario, you can abuse that, like in this case, where you could potentially abuse the fact that the kernel behaves a little bit differently than your userland process. The third one they call is just dangers and signal handler. So when you run in the async mode, the kernel is going to signal your process that, hey, something happened, and you have the opportunity to handle that signal. So you can just ignore it, or if you have a vulnerability in the signal handler, like maybe setting it off into a busy loop so that it's never going to complete or whatever, never going to actually execute and deal with that, you may be able to, or if you can corrupt its state somehow, basically some signal handler, depends on how it's implemented, could in theory be corrupted in such a way that it just won't handle the MTE signal. Again, that's only with the async case, but it is definitely a viable or likely case in a lot of applications. They do have the signal handler for that, usually for dealing with other issues, but they will have a signal handler, so there is that potential of a corruption allowing them to effectively disable MTE on their own thread. And then the fourth one is they're calling just a generic bypass in multi-threaded environments. And I thought this one was kind of cool because basically the way that they'd bypass it is with the kernel, it's only going to flag your thread as having, again, when you're running in async mode, it's only going to flag your thread as having had one of these access errors when it reads that flag to see like, hey, it had this access error. And that happens when you re-enter the kernel. So if you enter the kernel or whatever, or avoid entering the kernel, actually, if you can avoid entering your kernel after your bad access, that flag will be set, but the kernel's never actually going to send you the signal saying, hey, MTE happened. So if you could have all of your work by the exploit done on another thread, so say you have one thread actually make the invalid access and another thread then reads the data that was accessed and can get all the information, you'd be able to bypass MTE. So you kind of have that window where, and they actually kind of have this set of rules for MTE safe exploitation. One being that the exploit needs to complete or disable MTE without needing to make a system call from the faulting thread, and kind of a time window for it. If you want to have acceptable reliability, needs to run within what they estimate as 0.2 milliseconds. And that's just because of your general interrupt rules, just because the scheduler's quantum interrupting your process every about 4 milliseconds. But yeah, so that's kind of the big issues that they've spotted with MTE as how it exists with the Android or Linux kernel. And that I thought was the most interesting part of the set of posts. Like I mentioned, they do have these case studies in the second post. Has this interest table saying like in a Chrome render exploit, how likely is to have like a no intake bypass of some way, like speculation or whatever of leaking it or having their unknown take bypass. Again, terms that they define right at the top there, but they have that. It is kind of interesting just to see how the different areas, and as you'd kind of expect, a messaging application one-shot exploit is going to have a much harder time dealing with this than having something where you kind of have that back and forth call. But one-shot exploits are pretty hard to pull off already. So with that limitation, it's not that surprising that MTE will also be much harder to pull off, or MTE bypasses.
Yeah, I
Um,
mean, as a whole, the way I've looked at MTE is mainly a hit on reliability.
yeah,
So in any situation where you don't get multiple attempts, that's gonna kind of compound, right?
yeah, exactly. Um, so the third post kind of goes into the kernel a little bit, talks about like some of the issues that they'll have in the kernel, with actually
Mostly with
implementing.
enforcing MTE in the first place.
Yeah, with trying to implement it, like they mentioned that they need this the translation control register, this TCMA bit or bits, can basically will impact when MT is on and off. So they basically disable it, do some things because the kernel needs to produce untagged pointers. It needs to go from like a physical address to a pointer, and it's not going to know the tag for that. As an example of how the kernel does need some functionality that isn't going to, or that will temporarily disable MTE, and that means that the kernel necessarily is going to have these primitives that can or that can uh, produce or forge pointers. And so they call out some things like DMA and using non-MTE enabled cores, so like attacking of the GPU with its DMA and stuff as just another thing. Being
Yeah,
kernel is going to have that tag fault status register, so they can potentially just like clear the fault from having existed. Also, things of that nature. Again, if you're interested in that, you can read it. It is like this is a really good set of posts. Probably the most in-depth look at MT I think I've seen. So
definitely.
like I definitely recommend giving this a read. But most interesting part I think was that first post, looking at here are some of the core issues that are practical that are likely to be run into. And while async is weaker, I think it's the mode that we'll likely see more often just because it is much more performant.
Not only
Um,
performant, but also less power consuming. So this is something the posts don't really go into, and I think it is part of why we haven't seen MTE get as much adoption as we might have thought, is that when you're talking about ARM devices, one of the big selling points of ARM is the power consumption, which is why it's good for like mobile devices like phones. And when you have something like MTE where you're adding these checks on every access, it does add quite a bit of power draw as well as a performance hit. Whereas the async mode, where it's only setting the bit and then it can check that bit at its own leisure, like on like a watchdog type scenario, um, your performance and power draw impact is minimized. So I agree. I think async mode will probably be the dominant mode, at least until the performance impact and power impact is reduced on synchronous. So yeah, I think that's a fair assumption to make. But yeah, a lot of the stuff we've seen on MTE in the past, like when we watched Andre's talk when he did that, the issues were more like surface level, right? Like the lack of entropy in the tag space, like the tag space only being 16 possible values, or the fact that the granularity was pretty large. If I remember right, the granularity is like 16 bytes. So if you have an intra-object overflow, um, that's not going to be caught by the tag check. But this goes a lot deeper on how you could bypass the mitigation as a whole. And some of these totally make sense and were kind of things that I think I would have tried, especially on the kernel side with using things like the coprocessors and DMA, because it's kind of obvious, right? There's going to be devices that have to access memory that aren't going to be implementing tag checking. But then like some of them I thought were really cool, like the idea of using syscalls on user space to either oracle the tag or to just bypass it entirely, I thought was a really cool idea. I'm not sure how practical they are. Project Zero seems to think they're probably not too practical because I think they said the security impact is minimal. And I'm assuming the reason for that is if you're in a position where you can utilize syscalls to do this as an attacker, like that's a pretty difficult position to get in. Like MTE will have hopefully stopped you before you can get to that point,
yeah, fair
if
point.
you're on the defensive side. But the other issues like issue 3 and 4, and like you, the the fourth issue was the one I liked the most, where you could, uh, just not context switch and abuse preemption to accomplish your exploit steps. Those are pretty interesting from a security perspective, and I think there are some scenarios where you could leverage that. Um, you would need a fair amount of control again to be able to influence like the scheduler and whatnot to bend to that. Like stopping your own thread from entering the kernel is not something that's going to be very easy to do in a completely unprivileged context. But it's definitely worth considering, and these posts do a really good job of laying out the kinds of things that could bypass MTE and how fixable they are. Like with the syscalls one, they mentioned that could probably be fixed in the kernel by just changing how the syscalls interact with userland tagging. But like the things with signaling and stuff, that's going to be a lot harder to address. So yeah, like these posts are, as always from Project Zero, like really excellent and thoroughly detailed. And I think vendors and whatnot are going to be in a better position to weigh the trade-offs of if MTE is worth it, and if it is, which mode is worth running with information like this.
Yeah, and actually, one of the attacks they didn't totally mention here, and it's semi-related, is that you may just be able to use like a single write, or this was in the kernel section as like hardening, but being able to disable KSAN from executing. And I don't know if it's really been adopted that anything's running, like any device is actually running KSAN yet, but there is the look at with MTE, they may actually try and run KSAN on like production kernels. So with that,
Like kernel address sanitization, sorry?
yeah, using
Okay.
so it's using the hardware based implementation, so using the tagging, so it's not as performance heavy as normal KSAN, which is the
Oh, right,
significant
yeah.
hit. It's a weaker one that uses the tagging, but just being able to turn off KSAN in like a in a single write would be a primitive now that you kind of need to be a bit more, I guess, worried about. But yeah, that was just something I skipped over and just remembered it.
Yeah,
Um,
it took me a second, but when you started going through it and talked about the tagging with KSN, I remember what you were talking about. Um, yeah, I totally forgot about that too, to be honest. So,
and also since you mentioned, I think it was Xeri's talk. Yeah. I'll add that here into our show notes. Really good talk overviewing a lot more directly, like here's how MTE is being implemented, here's what it does, and here's how we're trying to use it. Really good overview from the Linux Security Summit a couple years back.
yeah, I think that talk goes really well together with these posts, because that talk gives you the basics of what you need to know, the service level overview, and then these posts will give you the all the nitty gritty details of um
The security.
the potential holes. Yeah.
Yeah.
All right, so moving into a post with a bit more of an inflammatory headline, we have TPMs provide absolutely zero security, or provide zero practical security. So this was a post I'd seen over the summer. It was posted in a Discord that I'm in by the author, actually. It garnered a fair bit of attention. I don't think many people read past the headline, or at least the first paragraph. So um, I did want to go into it because it does raise some interesting points that I hadn't really considered too much before. And also, it just gives a good insight on the TPM, like what TPM does, I guess, because there is a lot of misinformation or just lack of information on how TPM works. And in the explanation of their opinion here, there's snippets that are pulled out of the TPM spec and boiled down to what they actually mean beyond the engineering speak. So I think it's useful for that too.
There are
So
some useful things. I will say though, I felt it a few times. It felt like he was kind of just taking the weakest form of TPM and attacking that. Um, as an example, like over the years in contract, I've occasionally been provided a laptop by a client, and like I'm supposed to use that laptop to access, all their stuff, VPN and all that. And every time I've had TPM with a pin, like with full disk encryption, and the pin was not numeric, it was a full password pin. Every single time that's happened, and yet he calls that out as being a rare case that takes a lot of extra work. So it might be I haven't tried to do it. But he calls that out, whereas my experience has been that's the only way I've actually used that. So it just felt a little bit weird there, but that's purely my experience, purely anecdotal, and not something just to base it on. But I did feel a little bit like he was taking the weakest options throughout. But I'll let you actually go through it.
Yeah, so it is a bit of a rant on TPMs. And the core premise of the article is that TPM doesn't accommodate the threat model that a lot of people or organizations claim that it does. And it's too easy to subvert, especially from the context of a physical attacker. So, first off, I'll give a bit of a background on what TPM is, as the article does. So, TPM, Trusted Platform Module, much of what brought attention to TPM technology was Windows 11, as it required it to install Windows 11. And you can think of it as like a secure device that stores keys and has a controlled access channel to those keys. And the idea is those keys can only be unsealed and used if various qualifications are met, such as the boot integrity with measurements. And that's where attestation comes into play in performing measurements, where boot components will be hashed and then verified by the TPM, which will record those measurements, verify them, and then only unseal the final keys when needed and when all of those measurements have been proven. And this is pushed for especially in things like enterprise and cloud, where attesting the boot process for a machine isn't compromised is pretty important. And lately, it's been pushed on consumer devices as well for attesting that the operating system you're running was loaded in a clean way, like wasn't compromised by malware or something. Now, again, something this article does well and that I really like is that it breaks down things from the TPM spec, which is really dry and difficult to read. And I think this article is a good recommend for just understanding how various parts of TPM and like how they work and what part it plays in the boot process. I am going to skip a little bit of that here, as the where does it break section is where the argument really comes into play. So here they go into an overview of a typical Windows boot process on an Intel device with full disk encryption, though AMD is fairly similar. So the boot ROM will execute, load any off-chip firmware that's required. It'll fetch the BIOS, possibly verify the BIOS if boot guard and BIOS guard are enabled, and then UEFI boot will start. Various drivers will get loaded from OEMs and whatever, along with the Windows Loader and Boot Manager. And in that process, measurements are performed and checked on things that are loaded. And then finally, the NT kernel is loaded. And if the measurements pass for all of those things, the TPM will unseal the key for BitLocker for full disk encryption. One of the problems, though, is if there's like vulnerabilities that can be exploited at any stage in that process, future measurements can be faked and compromised, or you could just extract the key without worrying about the TPM at all. And we've seen some conference presentations and blog posts that have exploited various configuration issues or memory corruption or whatever to get access in one of the many OEM drivers and UEFI. And furthermore, in situations where the TPM is a separate dedicated TPM and not implemented in firmware on the CPU itself, the communication channel where the key can be sent across might be insecure. I've talked about this before, and we've talked about it on the show when some of the articles showcased it. But for BitLocker, for example, it's possible in some cases to just straight up pull the keys out of the plaintext data streams going across the SPI bus with like a logic analyzer, FPGA, or whatever, due to the lack of encrypted parameters. So that's some of the weaknesses with TPM. And once that key is compromised, until the key is changed or whatever, like the attacker would have access to your data going forward. It's like a one-time break. It's going back to like the soft and hard mitigation terminology that Project Zero used. It'd be more of like a soft mitigation. So that's the main argument of the article. I don't necessarily agree with all the opinions that are expressed. The concerns with physical attacks and software vulnerabilities compromising the measurement process are valid. And I think that's the main point the article tries to get across. The TPM doesn't secure the boot process as well as vendors would have you believe. But it also argues that TPM has had a lot of effort like wasted on it. And I think that might be a bit of a perfect is the enemy of good type scenario, where yeah, like TPM technology is probably oversold in what it provides, but it does add an additional step for attackers, and in some cases a fairly significant step. And the problems that it has can be addressed and improved upon. I think where Microsoft's putting a bit of effort there is with Pluton. I'm not going to go too much into Pluton here, partially because I don't fully understand it myself. It's not documented very well. But Pluton can act as both a TPM and complement the TPM. and tries to protect against some like physical attacks like fault injection and things like that. But yeah, overall, I wanted to shout this article out because it is a against the grain perspective. I think it is worth a read, and despite the inflammatory headline, which was done intentionally, like you can go down in the comments and see that was intentional. I think there are some valid arguments in here, and there's some good information as well, and yeah, it's just nice to have more opinions and more info on TPM because like I said, there's a lot of misinformation out there about it and a lot of like bad opinions. So, I kind of sound like a dick saying that, but there are some bad opinion, like very uninformed opinions, I guess I should say. But this is an informed. I think it's an informed opinion. So I wanted to
Yeah,
give it
and
a shout out.
unfortunately on my side, like I'm not really in a good position to make any arguments on here because I don't know much when it comes to this. I know a bit on the use case, like I know he focuses here on full disk encryption, which just for performance, like because TPMs can provide on chip encryption where the key does. You were talking about the plain text communication channel earlier, where the key doesn't actually come out over the plain text. Um, and it just does all the crypto on the chip. However, that is much slower, and something like full disk encryption, you don't want to be waiting for like every file access to be hitting the TPM chip. Like it's just not practical, and so it has to send it out. But there are other use cases that are less focused on in here, where TPM still has an option. That said, I think in his focus on where are people actually talking about TPM, like a lot of the time it is full disk encryption, and so it is a very valid criticism of it. Also, I will thank Gar7 for the huge raid. So welcome in, you guys. And yeah, tying it back into the TPM stuff. I mean, I don't know enough to make a good criticism here, but it did seem fairly balanced. Like, yeah, the title was pretty much set up to it was set up to make you click. It's very much a clickbait, but the rest of the post feels a lot more balanced.
Yeah. So, getting into a fun compiler issue, Meta Red Team X put out a post on GCC's failed stack protection on ARM64 targets, and it was a little bit surprising it seemed to have taken this long to spot this issue, but yeah, it mainly comes into play with dynamic size stack allocations. Z, I'll let you jump into it.
Yeah, definitely surprising that it stuck around, or that it wasn't detected sooner. Although, do they have a full timeline on when this was introduced? I was more focused on the bug itself. I didn't look at its timeline. Did you happen to pick up anything about the timeline here?
I don't
I
think anything was said explicitly about it. I just believe that it says all versions of GCC are affected, so I believe it's been ever since GCC has
yeah,
supported ARM64.
for a good while. And yeah, it's a fundamental problem with the fstack-protector flag on AR64, which is effectively so. The way the stack protector generally works, or the high level idea of it, is that it'll add a canary onto the stack. And so, if you're doing a classic, stack based buffer overflow, you're going to overflow that other data on the stack. Specifically, you'll overflow, or they'll place this canary so that you overflow, you change its value, and then when it returns, it just checks, hey, is this canary value still correct? No. Let's crash the program or signal it or whatever, indicate that a buffer overflow has happened, and don't actually try executing whatever they overflowed with. Um, and in terms of being a protection, like it does have a performance hit, so it's not common to use that like everywhere, but it is common to use that on some functions, especially things that are processing, network code, having large buffers on the stack. Um, and sort of things like that. So high level idea is just to prevent that sort of stack smashing where you can't reach the so you can still do local smashing where you attack like other variables that are on the stack, but not the actual return address. But the canary is supposed to protect your return address. So what they found on AR64 is that it uses the position independent code that actually implements a stack guard just assume or treats the stack guard as a local and just puts it first and kind of makes some assumptions about what the stack layout will look like. The problem is on AR64, the stack doesn't quite look how it would everywhere else. In particular, what they have is you have kind of a normal thing. Before you have the call, you're going to have the incoming stack arguments. That's pretty normal. You make the call, you have your local variables pretty early on there, have some registers saved. And the one thing that's kind of odd here is the fact that you have the dynamic allocations kind of in between here, where you have your local variables and then you have dynamic allocations. So these are things that are dynamically sized things on the local stack. So like your random int on the stack is going to be up as a local variable, but your dynamic allocation, dynamically sized stuff, will be later on down here. And so the problem is it inserts the canary right at the top of your local variables. It's assuming everything's going to be local, it's all going to be there, and all the registers would be after that. But where they actually, the main register that we kind of care about here is the LR register, which is going to be your return address. Well, saved register. I mean, this isn't the literal register there. So with the canary being up here, and sorry for those of you listening, but with the canary being up in the local variables and the dynamic allocations being allocated down here on the stack, if you have an overflow in one of these dynamic allocations, it can smash all of these values up until that canary without tripping the actual canary. So it can overwrite the pointer or the return address, and there's no canary stopping it. It will stop if you had an overflow in a local variable. You will kind of come around here, hit the you'll end up hitting that hitting the canary. But in this case, dynamic allocation specifically won't hit it. So that could be one reason why it wasn't detected earlier. It does have to be a dynamic allocation on the stack, not just like a random array on the stack. Although the dynamic arrays on the stack are the more likely ones to also have overflows because they are dynamically being sized. There is some extra work going on there. But yeah, just kind of a weird bug owing to the fact that position independent code implementing the canary makes some assumptions about make some assumptions about where and what the stack frame is going to look like. AR64 violates those assumptions, creating this gap in what's actually protected.
I will say in general, it's pretty rare that I come across dynamically sized stack
It
allocations.
is. That's why I think
At
it
least
could
in code
be.
that I've looked at.
No, it's rare. Like the amount of people who would even know like about the alloc A function, know to like call that to create one of those arrays. I feel like a lot of people just don't even know about it.
Yeah,
Um,
I've seen it once or twice, but not on ARM. I've seen it on x86. And in fairness to GCC, like this way of laying the dynamic allocation so far away from like local variables, it is kind of weird, and I can understand why they would want to make the assumption that uh, the stack cookie should always be placed right before or at the top of local variables because like there's so many different architectures, right? And where most of them would follow that pattern, that seems like a good catch-all. But in this specific case, that wasn't the case. So yeah, it's a fun bug. It's one that probably doesn't have a huge security impact. It would definitely make some vulnerabilities exploitable where they otherwise might not have been, or like reduce the requirement for having an additional bug or something. But uh, yeah, it's fun how it happened, and it's pretty rare that we cover compiler bugs in a case that's relevant for security. A lot of the time when we've seen papers and whatnot looking at compiler bugs, I like sigh. I'm like, oh, this is like not security relevant at all. But this is the rare case where we can talk about a compiler bug. So
yeah, I mean, it was just kind of like I saw this in my feed. It's just like, well, that's unexpected, because you don't expect to see it at that level, like in the security mitigation being the actual issue. Or Well, not
Yeah.
doing its job, I guess. Undefined BH mentions alloc is already a code smell in general, and yeah, absolutely. Um, there aren't a lot of good reasons to be putting dynamically sized stuff on the stack in the first place. I mean, there is when you want to do like malloc list code and stuff. Like there are some performance reasons because obviously it gets freed in a sense. Um, when you leave the function. So like there are some benefits to it, but generally speaking, you just wouldn't expect to see code written that way in general. But yeah, definitely code smell when you see it.
Yeah. So, revisiting Project Zero put out a post on analyzing a modern in the wild Android exploit chain, specifically the kernel components. So, this does all assume that system server context has been achieved, which is a fairly privileged context. To get to system server, the chain used some endays, including a Chrome type confusion for RCE, Chrome UAF for sandbox escape, and a Mali GPU driver logic bug that gave write access to read only pages to escalate the system server. From there was two more bugs that were utilized, and is what's more detailed in the post. The first vulnerability was a bug in the advanced Linux sound architecture, or ALSA driver, and was erased in the legacy compatibility layer for sound control element read and write functions. And the backstory for this is kind of funny because ultimately the cause of this bug was a refactor where the locking was moved from these internal set LM functions into the LM write function into the write user. So they basically like moved the locks one level up. And because of that, the locks were effectively dropped entirely for the 32-bit compatibility layer. And then in March of 2021, the locks were moved back to the internal functions where they were before. So that kind of fixed the issue. But because that wasn't a security fix, that was just like a refactor, that didn't end up getting backported. So there was a race UAF read and write on the sound K control object through these read and write ioctls. The second vulnerability was a Mali info disclosure
Just
where
before you
timeline streams.
change exploits, I did want to comment
Yep.
on that race there. I felt it was almost a little bit surprising because oftentimes when we've talked about these compath layer bugs, like 90% of the bugs we've talked about there, probably like 99%, have been info leaks, have been just dealing with the issues of being a compath layer function call where it translates from
Like
32 to
leaking through
64
padding
bit.
usually.
Yeah,
Yeah.
that's been one of the more common things that we've seen. So seeing it as, straight up being a race condition was, definitely surprising to me here.
Yeah, and it was all because of that refactor, which got undone anyway. So I thought that was a pretty funny backstory for that bug. So they had the UAF read write through race condition. The second vulnerability they chained with was for an info disclosure, and it was through the Mali GPU driver. And this was due to the fact that timeline streams for tracing GPU operations would ultimately just leak kernel pointers to user space. Just kind of a design flaw there. This was fixed by I put fixed in air quotes. It was fixed by preventing unprivileged access to TL streams, but for a while, TL streams were just accessible to unprivileged. So by combining the two, they could heat spray with Mali soft jobs to reoccupy that sound K control space, and by combining with the TL streams info leak, they could fake kernel pointers to get control over various fields, including the put function pointer for code execution. Although that is not the way that they went about abusing this. Ultimately, they left the put function pointer as it was, and realized that the handler for put would do a mem copy to a destination that they could control through the K-control's private data, which obviously they could corrupt with the use after free. So they use that to get a temporary arbitrary write. And I say temporary because it's not a very reliable write. It would require triggering the race every time and such. So for their final primitives, they use this arbitrary write to fake an FOPS table for the ashmem driver, which is the Android shared memory. And there they basically cause a type confusion. They overwrite the read and write file ops to that for the config.fs read and write, which causes a type confusion on the private data and allows you to do the read and write operations for arbitrary read write through corrupting private data, because they can control that through the set name functionality of ashmem. So yeah, this chain has some cool tricks. That said, it doesn't seem like a super good chain. First and foremost, I don't even know how this works on any devices that have kernel CFI enabled. As soon as you try to corrupt these file operation table pointers in the exploit strategy, the kernel should just blow up. So I'm not sure if the Samsung device that was targeted here just didn't have KCFI enabled, which would be kind of weird because I think it's been in Android at this point for quite a few years now.
So
Um,
I'm not sure about that since they do and I don't know if this is going to answer exactly, but because they do kind of corrupt it before the off, because the ashmem stores a pointer to kind of an FOPS that then gets used to create the FOPS for the actual, like when you actually open something. Um, and so because there's kind of that delay where you corrupt kind of the pointer or corrupt the data at the pointer that's being used rather than corrupting an actively used FOPS.
well,
Uh,
they do forge like a file operations table though, which they shouldn't be able to do.
they
That should
forge it
be
and then get to use it though. They're not corrupting like one that's actually being used as FOPS until they've corrupted and then they use it as the FOPS. So that's kind of where I'm getting at might be, and they are using a valid read file function. Like they're sending it to the config, so it is a valid target. So I don't think KCFI does a very deep introspection of what function calls you're allowed to go to, but they are using a valid read and write file function too. So even on that basis, it would still match.
Yeah, I'm trying to look into that because I know the kernel CFI is like Clang base, um, which I think you can have high granularity on, but I'm trying to see if I can find out exactly how fine grained it is. So
Yeah, I
yeah,
mean
maybe I'm just overestimating CFI's ability to catch this case, but I feel like CFI should be able to, at least if it's configured uh, in
yeah,
one of the like stricter modes.
my understanding is that's really just limiting you to calling functions. When it is there, just doing the whole prepend byte to mark your target sort of deal. That's my understanding of. But yeah, I'd really have to look into it. I didn't even think about CFI when I was reading this post. I don't think they mention it as really being an issue at all. Wasn't something I'd really thought of. So can't say much uh, on that aspect. 'Cause I'm just kind of doing it on the fly, but um,
Yeah, I'm just looking for indirect calls. It can use like function signatures using like the mangled name and everything, but yeah.
but I don't think it does. Like not in KCFI. Like because Clank CFI is a bit more like so KCFI is provided by Clank CFI, but I don't think KCFI uses all of the functionality of Clank CFI.
Okay, so it just might be one of those edge cases. Which to be fair, like when I think with Android stuff, I just assume for the most part that CFI is in play and would try to work around that. But yeah, maybe this one just slipped through the cracks on that.
Yeah, I've just
Um,
included a link here that goes to like the Android page talking about it. I guess this is really short. I was thinking of a different page. Um, yeah, I'm pretty sure there is like a good documentation about CFI for the kernel and how they're actually doing it. Maybe it was this one. No, that's still shorter than I remember. Whatever.
Try to find
They
it afterwards.
yeah, they did use one kind of interesting trick that to know when they're so they had the initial unstable corruption there, that arbitrary right, kind of unstable, hard to know when it actually lands. So I thought it was kind of fun that they targeted the uname a data. So when their corruption landed, they were writing their data into the same pointer that was used to fulfill like the uname a request, which would then give them kind of insight into the corruption. And to know when their corruption actually landed, like when they won the race and got the right to happen. Which I thought was just a fun use of that, just like a nice little string that's going to get echoed right back to you.
Yeah, I think there were some fun tricks in the exploit chain, but I'm curious on how reliable it was. I don't think they really comment on like the reliability portion, um, and it does rely on a few additional bugs where I think if you probably could bypass the need of those, like with the especially given the fact that you have the race read write. I feel like you might be able to derive your own info leak there, but I'm not 100% sure. I'd have to like play with the vulnerability to determine that for sure. But
Yeah, and they
yeah,
did take like this generic bug that worked just across the kernel and then use the spray strategy through Molly, which requires you have a Molly device.
yeah,
Which
it does kind of limit the applicability of the chain, but
yeah, it feels like they should be able to run like that unstable spray, like or not spray, or read write multiple times. So they do have a way of disclosing when it hits. So this could be an exploit that maybe takes a little while to run, but not necessarily making the device too unstable. So you have that, so you know when it's hit, you know when you have the corruption, you have a very clear info leak with the Molly TL stream data. Um, where some user controlled data is. So you have like a very clear info leak. You have a way of knowing when the race is actually hit. And well, at least for that, where you then have data in known location. Yeah, they don't talk about it, but I feel like it could be relatively like have a pretty decent reliability. I don't know about the time, but outside of the time aspect, it feels like it shouldn't crash on you.
yeah. As always, like I'm looking for things that aren't covered in the post because I'm just curious about them. But yeah, I'd be curious on like the reliability and some of the other circumstances. But nonetheless, it's nice getting information like this on what's being used in the wild, and pretty much Project Zero is the only people doing that. So yeah, nice to see another in the wild post because I think it's been a little while since. I mean, obviously, it's been a while since we've covered one because we were on break for the summer, but it's been a while since I've seen one as well. So
Yeah, I
yeah,
mean, there was the Edge, like Microsoft's team. I feel like they haven't posted in a while, actually. 'Cause
I
otherwise, we'd
think I
have
know the
probably
blog you're
covered
talking about.
something.
I
Yeah,
think there's
like
like two or three posts there, and then it just never went active again.
they kind of kept access, I think, going for a little while.
Did they? Hmm.
Um, yeah, I've just got the blog here now. It looks like their last post was February of this year, though. But they have like a couple pages here of posts. Oh, no,
Ah,
I
fair
like that
enough. Yeah, they
blog
have more
though.
posts than I thought.
They had really
Yeah.
good stuff. Fortunate.
Mm.
Looks like they're probably dead. I mean,
Yeah,
the
that sucks.
MSRC posts more, but they tend to post a lot of really high level stuff. I don't know where to find a good feed of just their research.
Yeah. So that's pretty much all the topics that we have. I do have a shout out from Impala Labs. So Impala Labs, I have the tweet linked here since the tweet, or rather the thread goes into a lot of the links. Although when you're not logged in, I guess those don't show up. So yeah, thanks for the Twitter changes. That's really excellent. The entire reason I brought up the tweet is not working on the stream. But anyway, they put out a bunch of advisories for bugs in Huawei Trustlets. So these run inside of the trust zone. Um, I had a bit of a personal interest in this because it's kind of close to what I'm looking at, although not on Huawei, but similar technology. You know, you're talking about trusted execution. A lot of the bugs were pretty simplistic and dumb, like integer overflows and things like that, and there was a fair amount of them. So I didn't want to do in-depth coverage of all of them. But especially if you're more interested in like the secure applets and stuff like that, some of these issues might be of interest to you. And they could have some, could do some like variant analysis type stuff on maybe some other devices. So I wanted to shout it out. Just check out what's interesting to you, but a lot of them are like pretty straightforward buffer overflows and a lot of variants as well. So
Yeah, which I
yeah,
mean, honestly, with these trustlets, it tends to be the
seems to
case
be
that
common.
they're pretty insecure because they just rely on the fact that it's really hard to test and debug.
Yeah. So yeah, that's all the topics we have for this week. Thank you everyone who tuned in, and again, thank you very much for the raid, Gar7. Welcome in everyone. Hope you guys enjoyed it. We do these podcasts every Monday and Tuesday. Monday we cover bounty topics. That's at 3 p.m. Eastern, 12 p.m. Pacific. We go into more web level stuff, and then Tuesdays like today at 7 p.m. Eastern, we go into the lower level topics. So yeah. So that was the podcast for today. Again, thanks goes out to everyone who listened. You can check out our past episodes on Twitch and all of them on YouTube, Spotify, Apple Podcasts, more links on Anchor. Feel free to join us on Discord and follow us on Twitter. Links to those are down below or in the chat as well. And yeah, we'll see you next week.